So welcome everyone to this IAM seminar. Today our speaker is Arun Kumar from the University of California in San Diego. And Arun is an assistant professor in the Department of Computer Science and Engineering and also in the Halit-Yolu Data Science Institute at UCSD. His research interests are in data management and systems for machine learning, AI, and data analytics. And he contributed to a lot of different developments, including open source libraries like Apache and products from several companies, including IBM, Oracle, Google, and Microsoft. And he received several awards early in his career, Sigmund Awards, an NSF Career Award, a Hellman Fellowship, and a UCSD OSTEM Faculty of the Year Award. And so today, now we will hear from him about Cerebro, a layered data platform for scalable deep learning. So thank you very much, Arun, and yeah, it's all yours.
Thank you for the kind introduction, Hendrik, and thank you for the opportunity to speak here. And thank you to the audience for joining. I'm impressed that Hendrik pronounced Halit-Yolu correctly, so that's awesome. I'm an assistant professor here, like you said. I've been here for about 4.5 years at UC San Diego. So today I'm going to be talking about some of our recent research on this scalable deep learning system. And this talk is tailored towards majority non-computer science focused audience. So if some technical terms or concepts are not clear, feel free to interrupt and ask me questions. I'm happy to keep this talk interactive. Okay, so I don't need to tell this audience that deep learning is now all around us. Everything from web search to social media interactions to e-commerce to machine translation to conversational assistants, they're all using deep learning methods to enable richer interaction capabilities. And it's not just the big commercial companies, even healthcare is now very excited about deep learning, especially radiology. A lot of research groups in radiology have pivoted towards using deep learning to identify diseases in many images. Wildfire monitoring. We saw the giant wildfires in California. Satellite imagery and remote sensing is now enabling unprecedented levels of monitoring capabilities to look out for wildfires. It's also being used in agriculture and so on. All of that uses deep learning. And of course, this is the material science seminar. So Hendrik and Yusu requested that I weave in some material science stuff. So I looked through some material science papers from ACS and so on. It was very fascinating to see how this material science and engineering community is embracing deep learning too, for everything from simulation data to actual kind of understanding properties of materials from their crystal structures onwards to across the entire scales of the materials compositions. In the Silicon Valley world, they call this AI is eating software. That's the adage. AI sounds very highfalutin. It's not, I'm not gonna call it AI. I'm gonna call this bunch of programs that process tensors, matrices, multidimensional arrays, and convert them to different multidimensional arrays. And that is what is deep learning. So for the rest of this talk, I'm going to talk briefly about more precisely what are deep learning systems. It's a new class of software systems that have come about in computer science in the last half a decade that have enabled this new wave of innovation in applying machine learning techniques. And then I'll talk about our platform, Cerebro, that enables a new approach to scaling deep learning systems. We call this multi-query deep learning. And then last, I will go deeper into one particular technique in Cerebro to highlight what sort of innovations are we coming up with that amplifies the capabilities of deep learning systems. And here's the rough time breakdown, 5 minutes on the first part, 15, 15. If you're already familiar with deep learning systems, feel free to sleep for the first 5 minutes. Okay, what are deep learning systems? Like TensorFlow and PyTorch, all of you probably have heard about it or working with it. Precisely, deep learning systems are software systems to specify, compile, and execute deep learning training and prediction workloads on large data sets of any modality. And the key thing to note here is any modality. They can apply to images, time series, text, tabular data, multimodal data. They don't really care what modality you give them as input. This is a key departure from a lot of analytic systems from the prior era. So let's break this down. Specify, compile, and execute. What does that mean? Specify from a computational standpoint means you write code in an abstraction called the neural computational graph. And then you train what are called parameters of this code using an optimization procedure called stochastic gradient descent. There are various flavors of SGD. Compile in a computer science terminology means you translate all those computations that you have specified in that neural computational graph into something that the machine understands more easily. It's hardware specific code. That's called compilation. Then comes execution. Once you have compiled it into some code, you now need to place that execution of that code and the data on the actual hardware, the devices that you use, processors, the memory, and so on. These sorts of deep learning systems allow you to do this seamlessly just by writing very high level code in Python or something like that using their APIs and handle compilation and execution for you. The world before this, just even a decade ago, this was not as seamless. People had to write very kind of cumbersome C++ code or something else to train neural networks. And so the presence of these deep learning tools has really revolutionized the ability for people to play around with all sorts of neural computational graphs. And so they have become this unifying software abstraction to convert raw forms of inputs into outputs of any form. Again, you could also do like image as a prediction task. But the art of deep learning lies in the way you do these layer-wise transformations of the inputs to the outputs. This is where people innovate in the core ML algorithmics world, in the AI algorithmics world. And these days, people are trying to infuse domain knowledge into these layer-wise transformations, for example, physics-based methods for reducing the complexity of these graphs. All of these layers are trainable. They have parameters. So just like you have your linear and logistic regressions that have parameters that you estimate from the data, these graphs have parameters that are estimated from the data. And there's a whole zoo of architecture names that you might have come up with. You might have encountered convolutional neural networks, recurrent neural networks, long short-term memory networks, transformers, graph neural networks, so on. They're all forms of neural computational graphs. CNNs in particular have become extremely famous. You can now tell apart cats and dogs very easily. I'm just joking. There's a lot more serious applications of CNNs. Transformers are now the state of the art for natural language processing. So for every web company that's dealing with review text or identifying posts that are potentially illegal or against their standards, they use these machine learning methods, these AI methods called transformers that are forms of deep learning. And you can see the architecture has become pretty sophisticated across all these modalities. And of course, in the material science world, there's a lot of excitement for all kinds of new architectures that can learn directly from the geometric representation of the inputs, the crystal structures, the material properties, the simulation results, all of that go as close to the raw forms of input as possible to weave in domain knowledge into these computational graphs. So as a deep learning practitioner, as a user of deep learning tools, how do you deal with this today? You specify your DL training tasks. Somebody gives you a nice architecture. Maybe Yusu tells you this is the architecture you should use based on the physics and the topology and stuff. Okay, you write it up in your PyTorch API. And then PyTorch runs this on a cluster for you. And what's a cluster? It has GPUs, it has memory, it has disks. And there's also, of course, CPUs. But deep learning, typically training, it requires GPUs as well. This cluster might be managed with a cluster managing service like Kubernetes. So this is sort of the world that most deep learning practitioners operate in. Any questions so far? Okay. The trouble is, this rosy picture is actually a false advertisement. Deep learning is never one and done. You have to sit and tune and experiment with all sorts of knobs. This causes a huge bloat in resource costs and in runtimes. If you want to use GPUs, they're not cheap. If you're an academic research group, you want to get the good industrial strength GPUs, you have to shell out to cool thousands of dollars for just one device. And now students will start competing with each other. Oh, I want that device too. And you will quickly run into enormous costs. And that's not tenable for academics. You might say cloud computing is making it feasible, but if you do the calculations for cloud GPU costs, it'll quickly explode. And that's not just costs. There's also energy considerations here. And this is from an NLP paper from a well-known name in the natural language processing world. And this paper says, if you look at a modern machine learning pipeline for natural language processing, the amount of carbon emissions, CO2 emissions it does exceeds the average Americans like 1 year carbon emissions, or even many times more than that, depending on how much tuning you do. If you don't do that sort of tuning, you're not going to get effective use of your label data. You may not get good accuracy. And it's not just the academic community that knows about this. The public press, the popular media is very kind of honed in on this. You can see all these sorts of news articles about how deep learning has become so expensive and it's contributing to the carbon emissions problem of the world and so on. What do these big giant corporations that publish all these, oh, we did this model on 100 GPU cluster. What do? This is what they do. If you go and ask them, they'll say, oh, we just throw more GPUs at it, more memory at it, more machines at it. I call this the gospel of gluttony. And all of these major technology companies, all these cloud giants, in the database world, we like to call them the whales of computing. This is what they're up to. If we follow their gospel of gluttony, we will burn the whole planet in holy GPU fire. We don't want to do that. And what my research is about is to rein in this bloat on resource footprints, on total costs, and energy that deep learning has brought about in the computing landscape. I call this democratization. Democratization to enable deep learning systems to be used by domain scientists, by enterprises, and many others without having to break the bank, without having to burn the planet. Use resources that you need, not resources that you can get. And be prudent about the way you're using the machine resources to achieve what you want in the way you want it without causing this sort of bloat. So that's the overall high-level picture of what my research is about. Any questions so far? No? Okay. So now we'll dive into what Cerebro is about, how we are going about achieving this vision. In Cerebro, the basic observation is the simple intuition. I call this multi-query deep learning. Model building is seldom just one model. Typically, there are multiple executions of models that are issued by the same user. For example, tweaking. You want to do these knobs called hyperparameters. You have to sit and tune learning rates, regularizers. Neural architecture is also a form of tweaking. You cannot just specify one computational graph and then say this is the best. You have to play around with it. You have to figure out which ones are suited for your task and for your data set, all of that. All of those forms of tweaking is like writing and rewriting your code over and over and executing it. And that bloats the resource footprint. There's jump starting. That's another form of building multiple models. Transfer learning is now front and center in the deep learning world, especially from images and text. Somebody else has trained a giant model on a giant data set for you. Don't start training your model from scratch. You can reuse parts of their code for yours, including the parameters in their code. And so feature transfer is one form. Other forms of transfer learning exist. When you do that, you'll have to try and kind of compare different ways of doing this sort of transfer. And then there's customizing it to your specific application. You may have a generic model architecture, but you might want to do ablation analysis. You might want to do feature selection. You want to understand from a scientific standpoint, what is it about the data that contributes to the outputs? Rather than just throwing everything into one giant black box, you want to dive into which parts of the inputs contribute to the black box accuracy. These sorts of things inevitably involve retraining and rerunning models again and again. Putting all of these together, I call them the model selection process. Model selection process is what the practitioner works with to make effective use of deep learning. If we take this higher level view of the model selection process, we will treat each of these models from a database parlance as queries. We call this multi-query deep learning. If you take this higher level view, turns out we can optimize a whole bevy of metrics that we care about. Runtime, you could finish your computations much faster. Memory and storage, you could make do with fewer machines. Network communication, on a cluster, you don't need to bottleneck all the machines. And even energy, you don't need to burn the planet. And so the rest of this talk, we will go about how Cerebro is planning to do all of this. Okay, to position what Cerebro's work is about, in case you're not familiar with the areas of computer science, it synthesizes and innovates upon three areas, traditional areas within computer science. Machine learning and AI, of course, you've heard about this endlessly, but there's also computing systems and databases and data management. And my training is in databases and data management. I have worked for a decade in the intersection of databases and ML and systems. And so I have this, what shall I say, tripartite worldview of how to approach this problem. From the ML standpoint, Cerebro enables deep learning practitioners to specify this model selection workload more holistically, rather than at a very low level of just running code one by one. From the system standpoint, we leverage techniques to automatically scale this workload across all levels of data and model scales. And that's something that people in the systems community have been wrestling with for half a century in the computing world. And so some of that insight, some of those principles need to be used in this context. And finally, all of that, we don't just want to scale and then do what the whales are doing. We want to do this prudently and efficiently. And this is where techniques from the database systems world called query optimization are used. And this is where we innovate upon coming up with novel forms of query optimization to improve the resource efficiency of this whole stack. Specifically, from a database parlance, the technical term is multi-query optimization. Okay, so what is the high-level cartoon diagram, the overview of Cerebro's approach compared to what I showed earlier? You still have you still have your Kubernetes cluster or whatever, or even just a single machine is fine. 90% of data analytics workloads, one machine suffices. But some of the most interesting bits are in the larger scales where you have to use multiple machines. So then you have a cluster. You still specify your model selection workload using the same tools, PyTorch and TensorFlow, using the same computational graphs, except you now give more holistic information about the model selection process, hyperparameter tuning, architecture search, ablation, and all of these other things that are inevitable in effective use of deep learning. We inject some software magic called multi-query optimization, and then we schedule the computations for you on the cluster rather than you manually running it on the machine yourself. So Cerebro acts as an intermediary between your deep learning tool and the machine resources. And this intermediary does a better job than what these tools do today in making effective use of these resources. What's more, now that we have decoupled this specification from the execution, we can now inject different execution backends for the same specification. If you're tired of using your Kubernetes cluster, your DevOps is not responsive, you want to run it on AWS, fine. Take your same code base, hook it to an AWS machine, Cerebro will scale it on AWS for you. If you already have a Spark cluster installed, you want to manage data, there's other databases sitting around, you want to do queries on that data as well, and you also want to do training, fine, you could train it on your Spark cluster as well. Now, Frank is also here. So Greenplum is another one that has actually been integrated for some of these techniques of Cerebro. That's a parallel relational DBMS. If you're familiar with what they are, it's pretty common in the enterprise world. But Spark clusters are pretty common in the Cerebro has been integrated with Spark clusters and Kubernetes. We are working right now on making it cloud native as well. So this is the high-level overview of Cerebro's approach to scaling deep learning workloads. Decouple the specification of what you want to train from the how you want to execute it, and inject multi-query optimization in between automatically. This happens transparently without you as the data learning practitioner being aware of how we are doing this sort of optimization. Any questions about this slide? Hendrik, Yusu? No questions on the chat, I guess.
Thank you very much.
Okay, great. So far, so good. So that's good. I think it's clear. Okay, now let's unpack this. What is the full vision of the Cerebro platform? What do I mean by specification? What do I mean by optimization and so on? This appeared in this research conference called CIDR in January. And so I have the link in the abstract as well. There's a 10-minute version of that video as well. This is an expanded version of that video, if you've already seen that video. High-level model building APIs are the specification layer. You could use your routine Jupyter notebooks, you could use command line interfaces, you could use graphical user interfaces. We are building new interfaces as well. Stuff that you're already familiar with. You specify this model selection process using these APIs for hyperparameter tuning, architecture search, feature transfer, sequence and graph analysis. We're building new ones. Machine learning over groups if you want to train models on subsets of data and so on. All of these are just a couple of lines of Python code. And these are already available in Keras, in TensorFlow and PyTorch. We are not changing the APIs. What we're doing is we're hijacking what goes on behind the scenes. Now, at the lowest level, we have the execution and storage layer. full Cerebro vision, we have direct file system access, including potentially with cluster managers like Kubernetes, data flow engines like Spark and Greenplum, like I said, and cloud native execution using machine resources that are available elastically, EC2, EBS, and so on the AWS side, and many more. We are agnostic to what the backend is. We are agnostic to what the execution and storage layer are. Our focus is in between the translation from the what to the how. And this is what we call the optimization and scheduling layer. We come up with new computer science techniques, do this whole translation very efficiently in a resource efficient manner so that you reduce resource costs and runtimes. Specifically, there's a technique called Model Hopper Parallelism that I'll talk about later today. There are various hybrids of Model Hopper Parallelism. There's capabilities for materializing data and models and memory management so that the user doesn't have to do it. Turns out that these tools, TensorFlow and PyTorch, really suck with memory management. They sometimes try to cache data as much as possible, and they might crash if you don't fit in memory. And I will talk about that in the next part of the next couple of slides as well. However, under the hood, Cerebro uses TensorFlow and PyTorch as its, what shall I say, lackeys. It calls out to TensorFlow to go and schedule computations on these machines. All it does is it wraps around TensorFlow to do it in a more efficient manner than what TensorFlow's distributed platform does, or same thing for PyTorch. We are not changing how the computational graph is specified. You still use your PyTorch API or TensorFlow API to specify the computational graph. We're just changing how you're scaling it. All of this happens in a manner that is reproducible, reusable, shareable, and on the cloud setting, it's also fault tolerant and elastic. What does that mean? If one of your machines goes down or gets disconnected, the computation will not crash. It'll still run, and the machine that lost its computation will be restarted later, and then the computation will be rerun. That's called fault tolerance. Elasticity, if you suddenly decide you want to do a larger graph analysis workload because you want to train larger models and you need more machines, you can elastically add more machines. Explanation engine basically allows you to make sure that the models that you're building, you keep track of them. And then if you want to do post hoc analysis to understand why it gave certain predictions, it'll optimize those computations as well. And finally, we have the metadata manager. Metadata is basically data about data. All of these processes that you're running, sometimes you might end up producing hundreds or even thousands of models. All of that needs to be tracked, archived, and annotated and managed, and it should be queryable, it should be visualizable. And so that's what the metadata manager does. So now you could post queries over the validation errors of your model selection process and then say, which hyperparameters give me best errors and stuff like that. And all of that are functionalities that are orthogonal to Cerebro. So we outsource that functionality to tools like TensorBoard and what is called MLflow. And these are open source tools that allow you to do provenance and metadata management. TensorBoard allows you to do visualization of learning curves and so on. So all of that is orthogonal functionality. We just plug into those to leverage them. Any questions about this? So now, yes,
yeah.
Yusu.
I have a quick question. So I'm wondering, so this platform is your own like interface, or like, so like, for example, if I want to use it, then I can just use it directly from Jupyter, or like I need to download the platform first, then you automatically kind of integrate all those tools you're showing here behind the scene? I'm just kind of a little bit confused, like, you know, if I use this, how can I use that?
That's a great point. So on the Cerebro project webpage, which I'll link, there's illustration and use case kind of examples and documentation. It's as simple as a pip install. So it's like a library, like a Python library. So you just install it. Now, the underlying machine resources, you will have to give configuration files to say, this is where the machines are, these are the IP addresses, these are the ports to talk to, that's how it. And the rest happens transparently to you. So you use the APIs, which look very similar to what the APIs are for Keras and TensorFlow in your Jupyter notebook. And then you run it under the hood. Cerebro will take care of the scheduling it on the cluster for you. So it will be as close to your existing workflow as possible.
Okay, so it will run faster, or it's, you know, or it's kind of like just more efficiently use the computer resources? Okay.
I'll get to that on the next slide. What Cerebro do that's different from what you will face today.
Okay, yeah, great, thank you.
Thank you for the question. Any other questions? Okay, so just to kind of wrap up this high-level overview summary, It's a layered platform with careful decoupled design so that your code can scale across multiple levels of machine resources. It's a unified platform for all kinds of data modalities and deep learning workloads. We're not image specific or table specific or text specific. And this translates to multiple benefits. Productivity, as a deep learning practitioner, as a data scientist, as a machine learning engineer, you can focus on what you want to do with DL, not muck around with how to scale it, how to optimize it on large scale machines. Scalability happens seamlessly. You can scale to any data sets and model sizes. We are still getting there, but that's the vision. Resource efficiency. Using these techniques, multi-query optimization, we can lower the runtimes and the resource costs, often by even 10 times compared to what you would do with just plain TensorFlow and PyTorch. And that could mean the difference between finishing in a week versus finishing in a day for training a giant deep learning model workload. Portability. And maybe the domain science folks may not be that particularly interested in portability, but in industry, it's a big deal. You don't want to get locked into one particular backend. And so portability means you can now use this on AWS. You could use this on, I don't know, Greenplum and VMware tomorrow, or you could just run it on an on-premise cluster. That's part of our vision. Any storage and execution backend should be possible. We also want it to be portable across any deep learning tools. So if you want to throw out PyTorch tomorrow and use TensorFlow, Cerebro, the rest of Cerebro can still work. Okay, so now let's dive into Yanxun's question. What kind of scalability issues arise and what optimizations does Cerebro do that are not present today? To understand this, you should understand the memory hierarchy. So I'm going to give a brief primer on memory hierarchy, computing systems 101. If you're already familiar with it, feel free to sleep for this one slide. The memory hierarchy are different levels of memory and storage for the machine where data is stored. Data, by data, I mean not just data sets, but also model parameters. And they are retrieved into the processor for computations. There's GPU memory, there's main memory or DRAM, there's local disk, and then there's remote. This is sort of the most common elements of a memory hierarchy in 99% of use cases. In some cases, there's also lower levels of the hierarchy, there are intermediate levels, but these are the most common. They have a huge spectrum in terms of various trade-offs. GPU memory, the data that's sitting there, is the fastest to access for computations. So as much as you can pack onto GPU memory, the better you are in terms of runtimes. However, it's the tiniest in the hierarchy. There's only a few gigabytes. And I don't know, maybe some people, sometimes people say gigabytes is not few, but I'm like, I've dealt with petabytes of data, so gigabytes is tiny. It's also the costliest in terms of the amount of dollars per bytes you pay. NVIDIA is now almost a monopoly. They are making huge tons of money by selling these GPUs. They can name whatever price they want, and they come up with these costlier and costlier GPUs that people are craving for. Capacity is still not catching up with demand. And then at the bottom of the hierarchy, you have local disk, which is the slowest to access data from. It will impede your machine utilization if you have to go read data from disk all the time. In between is DRAM. If your data is in memory, your processor can be utilized better compared to reading it from disk all the time. Unfortunately, it's also slowest. Getting data from the disk can be orders of magnitude slower than getting data from DRAM or from memory. And by orders of magnitude, I mean like really 100 times, 1,000 times slower. And so a lot of computing systems work is about optimizing across this hierarchy to make maximal efficiency possible. You want to get the fastest computation. You want to scale across this hierarchy so that your data or model parameters can sit across the hierarchy. Now, in deep learning in particular, because the workloads are so long running, often you want to use a cluster. Then you have remote disks, and that becomes even slower to access data from. Remote disks and multiplicity of clusters mean you're also amplifying your memory, storage, computation costs. If you're using 10 machines, it's 10 times more expensive than using just one machine. And like I said, 90% of workloads in data analytics can fit on a single machine. Sometimes you want to scale if you want to reduce computation, but a lot of the interesting problems exist at large scales. Okay, so let's look through scalability issues across this hierarchy. Number one, and one of the most common I'm hearing these days, is their model doesn't fit in GPU memory, or the data batch doesn't fit in GPU memory, or both together don't fit in GPU memory. What will happen today if you were using PyTorch or TensorFlow or tools like this? It'll crash, and you will struggle to fit this onto their GPU memory. And what I've heard from domain scientists was like they're actually changing their science to work around these bottlenecks of TensorFlow and PyTorch. They're like, no, we don't explore more interactions in the graph neural network because it'll just explode the memory footprint. Why? Because you're changing what you want to explore because of machine restrictions. That's not how it should go. The machine should work for your exploration. So this is one of the common scalability issues we encounter at the highest level of the memory hierarchy. And I actually Googled a little bit about this. Even in the material science world, people have made this observation. So this is a very recent paper from a bunch of folks. Some of these names are familiar to me, like Ian Foster is a well-known name in computer science. And they are applying even larger models for even larger data sets. Simulations produce huge amounts of data, imaging produces huge amounts of data, video produces huge amounts of data, and they are ever hungrier for larger and larger models and more parameter intensive models. It doesn't seem like that trend is changing. So clearly, this is a bottleneck that's impeding progress in a lot of domain sciences. What is Cerebro going to do? So this is something that we have already done about 3/4 of the way there. A paper on this will go out later this summer, in the next few months. But what do? We do something called model sharding and model spilling. This is a classic technique from the database systems world. If something is too big to fit on higher levels of the hierarchy, break it down. Move it to the lower level of the hierarchy, read only what you want into the higher level of the hierarchy. You might have heard this jargon called divide and conquer. This is part of divide and conquer in computer science. We do this automatically for you. You specify a neural computational graph with the parameters and all of stuff as you do today. Transparently, Cerebro will rewrite that computational graph, break it up so that you can store it in DRAM instead of GPU RAM, and then move it back and forth automatically, especially when you're doing model selection. And when doing so, we can interleave multiple parts of different models across different GPUs. This allows us to raise throughput. And throughput is a technical term, which means how many models can you train in a unit time, or how many batches of data examples can you train through in a unit time. And this allows Cerebro to scale to any size models and any size data sets in these sorts of regimes. It does not face the scalability bottleneck of model not fitting in GPU memory or data not fitting in GPU memory. Now, how exactly that rewrite happens, how exactly do we interleave all of that part? That's the computer science part. I'm not going to go into too much detail now. I'm happy to chat offline about that if you want. So Yanxun, does this answer some of your questions about?
Yes, yeah, thank you.
Great. Anybody else has any other questions about this? Okay, great. Next, let's move down the hierarchy. Data set doesn't fit in DRAM. Now, again, the larger the scales you go to, the fewer and fewer people that have this problem, but the more interesting and challenging the problems become. And here, data set is so big that it doesn't fit in DRAM. This is especially a bottleneck for certain flavors of deep learning. Now, for convolutional nets, transformers, this is not that big a deal. You can store it on disk. TensorFlow and PyTorch do this automatically for you. They just stage the reads from disk to DRAM for you. But there are these models, graph neural networks in particular, and these have exploded in popularity in the last few years that end up doing random IOs. What is random IOs? That's a technical term from database world. If you're looking into disk to get one piece of example from the data, and then you're looking into disk again to get a totally different piece of example that is stored somewhere else on disk, that is called random IOs. You do that repeatedly, you will end up underutilizing your machines, your processor will sit idle, you're wasting memory, you're wasting processor time. And this seems to be happening a lot in use cases where people are doing these layering structure on simulations, especially in the material science world. Again, I Googled some papers and I saw people are doing very, very fine grained simulations at the atomic scales, at the molecular scales, and there is structure involved. And that structure is often graphical. It's often three-dimensional and so on. It's not just a giant flat image of a cat or a dog. And so you need that structure to be captured in the model. And now the entire data set may not fit in DRAM. You might end up doing random IOs. And we are tackling this. We're in early stages over here using, again, techniques that have been studied in the database systems world for other forms of computation, which is IO optimization. You want to stage the reads to disk and cache as much as possible in DRAM. And again, we do this automatically and transparently. We will rewrite the DO computation, including the computational graph, but also the training of the stochastic gradient descent part to reduce random IOs. And to do so, we have memory management. Memory management is a component of software that handles how DRAM is used what data is stored at that level and what data is not stored at that level, but at a lower level in the hierarchy. And turns out when you have model selection going on, you can cache data in main memory and reuse it across many models in a more intelligent way than what these TensorFlows and PyTorches of the world do today. What does this translate to? This will again translate to better, kind of faster completion times, better resource utilization, and so on. And so this is work in progress. I'll keep you posted how this goes and when this paper comes out. Last one I want to talk about is at the lowest level of the hierarchy. Data is so big that it takes far too long for even just one node to finish on time. And if you're thinking what scale I'm talking about here, you're talking about terabyte-sized data sets, or even hundreds of gigabyte-sized data sets. It's so big that if you copy it across machines, even on a cluster, you're wasting DRAM and disk enormously. Like here at UCSD, we have a 100 GPU cluster called CI. We use that extensively for a lot of deep learning applications. And we use 8-node clusters there that we are working with public health researchers in the School of Medicine. They have accelerometer time series data. These are multivariate time series from HIP1 and RISC-1 accelerometers. They are labeled. They are about 800 gigabytes in size. 800 gigabytes is a lot of data. If you copy it across 10 machines, you bloat your footprint to 8 terabytes. And because these clusters are shared, you're being unethical. You're hogging resources that other scientists and other researchers and academics on campus might be using. So you're not being prudent in utilizing your resources. But this is what these tools expect today. They want you to copy the whole data set across all the machines and just eat up as much as you can. What do we do here? And this is work that's already been published. So there are papers that are out there. I will refer you to that. We came up with this technique called Model Hopper Parallelism. The basic idea, again, comes from the database systems world. We call this sharding. Don't store your whole data set on one machine. Break it up, divide and conquer, spread it across machines. And this is something that relational database systems have been doing for decades. Once we've done that, now we can again schedule interleaved computations of model selection across these partitioned forms of data to raise overall throughput. So now you can train more models in unit time. You can reduce the amount of resource wastage that takes place. Now, the hop comes from the fact that we move models around automatically across machines. And that's what I will dive into next. This is the one technique that I want to showcase. Any questions so far? No? Okay. So what is this one key technique? This is on the scalability part 3, which is data set is too big to fit on memory. Now, the use case that we targeted was one of the most common use cases for model selection, which is hyperparameter tuning, architecture exploration, and so on. You do the grid search, random search, and such on learning rates, regularizers, dropouts, all of these things. You might do some architecture exploration methods. There are automatic heuristics like Hyperband, Autochorus, Asha, whatever, that programmatically do this exploration for you. Regardless, whether you're doing it manually or programmatically, you're going to produce a huge number of model configurations or configs to train on your data set. Excuse me. And that is where we connect it with the multi-query paradigm, multiple models to train. What we looked at, the prior art, they were suboptimal. And so we devised a novel parallel execution strategy called Model Hopper Parallelism. So what I'm going to do now is position what the prior art does versus what we're doing different. The prominent prior art from the machine learning systems world was something called task parallelism. And this is something that a lot of ML practitioners do. They copy the entire data set across machines if you want to do, say, 4-node cluster or 3-node cluster. And then you place different model architectures on different machines or different hyperparameter combinations on different machines, and then you train it. Many machine learning researchers don't even do this automatically. They do this manually. Like one of my ML colleagues here, I asked, I won't say who, about how they go about it. And they said, I will give one GPU to one student, and then each student will train a different hyperparameter combination. They call this graduate student descent in the AI world, in the machine learning world. I thought it's pretty horrible, but that's the state of the art because these tools don't do this seamlessly.
So does it make a difference if they get along or the student doesn't get along?
That's a good point.
Sorry.
No worries. Okay, so what's the advantage of doing this? Why are they doing this? Well, it gives very high throughput. You can train more models in a unit time by using more machines. It is also very good from an accuracy standpoint. From a machine learning theory standpoint, you're doing what is called sequential SGD. You're training the model on the local data set on the worker. You're not parallelizing it across a cluster. Stochastic gradient computations are very hard to parallelize. And so you get sequential SGD accuracy. That's the gold standard. However, it has major disadvantages. It's not scalable. You're copying the entire data set. We just said 1 terabyte public health data set, 3 workers means 3 terabytes. Waste of memory, waste of disk. Sometimes you could store this on what is called a remote storage and read it over the network, but then that's a waste of network. And the amount of reads you're going to do could be 1,000 times higher compared to not doing it. The other side, in the database systems world and also in the operating distributed systems world, they study this paradigm called data parallelism. Divide and conquer. You break up your data set into 3 shards, place each shard on the worker, D1, D2, D3. And so they have independent set of shards. Now you train one model at a time. One config is stored on a server. The server broadcasts that parameters to all the workers. The workers independently do a pass over their local shard, get the model updates, and then send it to the servers. This happens back and forth for every epoch of SGD training. It happens for every model, one after another. This is great from a scalability standpoint because you're sharded and you're not wasting memory, network, or anything like that from a data sharding standpoint. You can scale this seamlessly to petabyte-sized data sets. This is, in fact, how relational database systems and data flow systems like Spark deal with petabyte-sized data sets. However, from a mathematical standpoint, from an optimization theory standpoint, doing this at the shard level, sending these updates between the servers and the workers does not converge, especially for highly convex models like deep learning. It's been shown that it will lead to suboptimal accuracy, and the accuracy gaps can be substantial. And so what people came up with in the systems world was systems like Parameter Server and Horowat. I'm just throwing out names if you've heard of them. They communicate between the worker and the servers at a mini batch level. But if you look at stochastic gradient descent practice, there are often thousands of mini batches in a shard and millions of mini batches potentially on a large data set. And that means you're going to have enormous amounts of communication happening between these machines, and that dramatically drops the throughput that you can get, even 10 times slower. And so you will be 10 times slower with data parallelism than task parallelism. We looked at these and we devised a new hybrid parallelism scheme called MOP. And that offers the best of both worlds without the disadvantages of either world. How does that work? MOP is fundamentally rooted in an insight from optimization theory, which says that stochastic gradient descent is robust to the ordering randomness of the data. Every time you train something with SGD, you have to randomly shuffle the data set. But SGD does not care what order that data set is in. You can do any random shuffle. And we exploit that as follows. Shuffle the data set, partition it across the workers, just like your data parallelism. So you've sharded it across workers. Place different model configurations or hyperparameter configurations on these different workers. And we start the first epoch of SGD in parallel. So let's say here in this example, you have 4 different model architectures or model configurations, hyperparameters, whatever, and you train them on their local shard for what we call one sub-epoch, 1.1. Then you hop them across workers automatically. And this automatic hopping is handled by Cerebro. Now the models will restart their learning on the new shard that they are on. So DNN1, for example, jumped from worker 1 to worker 2 automatically, and now it sees D2. Then it'll jump to D3, and so on. Every model keeps hopping around the machines until it has seen all of the data set. And this happens for one epoch. Repeat this for every epoch. Hence the name Model Hopper Parallelism. Turns out that MOP gives very strong theoretical guarantees. It's equivalent to sequential SGD. So you get the same or very similar accuracy as task parallelism. You cannot beat it. It's the gold standard from an optimization theoretical standpoint. We are not doing model averaging of shards. We are not doing parameter updates that are asynchronous and stale and all of these other things that a lot of systems folks worry about. We get sequential SGD accuracy, albeit in parallel. And from a communication cost complexity standpoint, again, this is computer science jargon I'm throwing at you, MOP hits the lower bound for communication cost complexity. You might have heard time complexity, space complexity, network complexity, communication cost complexity is also one of those aspects. To emulate sequential SGD on sharded data, you cannot do better than this, and that's a theoretical guarantee. from a complexity standpoint. You can do better in the sense you could do better compilers or better architecture hardware or something like that. But from a communication pattern standpoint, this is optimal. There's a lot of technical challenges in making this practical and scalable. We devised a resource-aware scheduler to allow for evolving model config. You don't need to say, I am going to shard the data only once. You could do it across all epochs. You don't need to say, these are all the configs I have. An automated machine learning heuristic can produce configurations on the fly for you. We support data replication, fault tolerance, elasticity. And all of this happens without changing the internal codes of these deep learning systems. The machine local computations for stochastic gradient and training of the model with backpropagation is what TensorFlow and PyTorch does. The parallel and the scalability is what Cerebro handles. So we kind of have this nice contract between these deep learning systems and Cerebro that doesn't require us to peer into the internals of these systems. What does that mean? That means if tomorrow Google releases a new version of TensorFlow or Facebook releases a new version of, I don't know, PyTorch that is industrial strength, that's even better than what's out there, we can just use this as a drop-in replacement for the older version of Cerebro, older version of TensorFlow and PyTorch in Cerebro without changing anything else in Cerebro. That's a software design pattern that allows for what we call backwards compatibility. Okay, so we evaluated this on benchmark machine learning workloads. This is from the paper. ImageNet is one of the standard benchmarks, 0.5 terabyte of images to 1,000 class labels. On the x-axis here is the learning epoch. On the y-axis here is the top 5 validation error, the benchmark accuracy metric. We are comparing absolutely state-of-the-art machines, systems. Harvard is one of the most state-of-the-art data parallel system. Celery is a task parallel system. There are many others out there like Dask and so on. They're all pretty much equivalent. And then TensorFlow offers native ones called model averaging and asynchronous parameter server, just fancy jargon for, again, a form of data parallelism. This is the learning curve for model averaging. This is the learning curve for Harvard. Lower is better, right? This is error. So the lower left you are, the better you are. This is the learning curve for parameter server asynchronous in TensorFlow. This is the learning curve for Celery. This is the learning curve for Cerebro. So clearly, Cerebro matches the best learning curves out there. That means it's effective from a machine learning standpoint. You're getting the best accuracy as soon as you can from a learning theoretic standpoint. Coming to system resource utilization and efficiency, if you compare the runtime and the memory footprints, let's take the 313 at the bottom, parameter server asynchronous, its runtime is 10 times slower than Cerebro. Do you really want to wait for 10 days instead of finishing your workload in 1 day? MOP compared to Celery, which is a task parallel system, they are comparable in runtimes because the communication complexity makes sure that the computation time doesn't change that much. However, look at the memory footprint of Celery. It's 8 times higher than Cerebro's. Do you really want to waste that much memory and disk on your shared cluster or your cloud machine resources? Overall, we showed that Cerebro offers the best combination of both resource efficiency and machine learning accuracy for deep learning model selection. And this is why we picked Model Hopper Parallelism as the heart of the Cerebro platform. It's resource optimal when we take all of these factors, accuracy, runtime, and memory storage footprint across the hierarchy into account. Any questions about this? Okay. So Cerebro is already being used by public health scientists, like I said, on the accelerometer data. It's like they have more terabytes of data from different cohorts, people in assisted living facilities, people with obesity. Now they're looking at kids in Australia or something like that. Bunch of cohorts where they're trying to apply our code for training, but also apply our trained models for their cohorts. And they're pretty excited about this. We are actually writing a second grant. It's already funded by an NIH grant. We're writing a second grant on the future of that public health accelerometer and sitting, standing prediction and exercise activities and so on. Computational physicists, we are starting a collaboration with them to understand large-scale simulation outputs where the data and model don't fit in GPU memory. Neuroscientists have large-scale video of brain images where they want to understand how brains work, and these data sets don't fit in main memory. And like I said, Frank is here. He's from the MADLib team. Apache MADLib is an open source library for scalable machine learning and other analytics on relational database systems on a system called Greenplum and Postgres. And it's now part of VMware, and we're collaborating with them too. They have adopted some of these techniques from Cerebro, integrated as part of their open source library that's being made available to some of their enterprise customers. We have open sourced all of the stack that we are building. Cerebro Spark is also a stack that we are using extensively for these domain sciences. More workloads, more optimizations, and more applications are coming soon. And like I said, physics and neuroscience, we're already working on them. I'd like to thank the Hellman Fellowship Fund, the NIH, the NSF for their career award, and VMware for their gifts, all for this project. So clearly a lot of organizations across all kinds of fields are pretty excited about this. And I'm also very excited about, having read all these material science and engineering papers, the potential for scalable deep learning to transform the science and the engineering of it. And I look forward to learning more about it. I'm very new to this field. As far as my high school chemistry and physics in this space. So I'm looking forward to learning more about it from you all and collaborating with you all to both apply Cerebro and scale some of these tasks, but also extend Cerebro in the future. Like, this is a mutually beneficial collaboration. That's why I came on board, because with the public health scientists, we published journal papers in their top journals as well for public health. And we talked about their use cases in our computer science publications as well. So it's a mutually beneficial kind of arrangement. And that's a wrap. So these are my terrific students who have been doing a lot of this stuff. So Supun and Yuhao are the ones who are leading the charge on Cerebro. Sita, Advitya, Kabir are also contributing to various other parts. UCSD has some terrific students. I'm really fortunate to work with these awesome students. Okay, so that I'll stop my talk and I'll take more questions. Cerebro is open source. There's documentation, there's examples on the Cerebro project webpage. All the papers I talked about are available on the project webpage. We have easier to read blog posts if you want a gentle introduction. And the code is available on GitHub. You can also follow me on Twitter if you want more updates on the project. And I'd like to thank these other funders as well, apart from the ones that funded Cerebro. Thank you, folks. I'll take more questions now.
Thank you so much, Arun, for this very interesting talk. So yeah, it's time for questions.
More questions from the audience.
Thanks, Arun. It's really interesting. There's some feedback. I don't know where it's from. I have a quick question. I know that you mentioned that this platform is really a uniform platform that supports different type of data modality and different architecture. But still, I mean, given that ultimately you have to, find suitable, say, strategy to access memory and so on, I'm wondering how does different, for example, data modality, I mean, is it better for structured data? Is for graph, is it equally effective, or even just some of the material data, I mean, can model it either as graph or sometimes it's just a collection of, say, atoms, right? So and also, what is the impact of the different architecture of the deep learning neural networks? Yeah.
Right, that's a great question, Yusu. So from the data access standpoint for scalability across the highest level of the hierarchies, some of these models like CNNs and transformers are fairly straightforward. And the reason they're fairly straightforward is they are what they call feed-forward neural networks, because they have these layers and they're sequentially dependent. And so if you want to do, say, chopping up this model automatically, the sharding thing that I talked about, just pick one of these nodes and then chop up that model there, something like that. So that's the way we are scaling it across the GPU memory. Now, coming to models that have more holistic dependencies, like a graph neural network that may not have the sequential feed-forward nature, that chopping part becomes non-trivial. And that's why it's kind of being automated as part of a system so that the user doesn't have to manually do it. Turns out that you could still do that. You could still do that as long as you make sure that the communication cost between the GPU memory and the DRAM is minimized. And so right now, what we are focused on in this automatic model sharding and spilling part is recurrent models and feed-forward models. But in the future, we're looking forward to working on graph neural networks as well. And some of these techniques that we're talking about for automatic model sharding might need to become more sophisticated. So this way we rewrite and put this across DRAM and GPU RAM might need to become more cache aware. And so then in that case, I think it will resemble the second part moved up to the first part, which is random IOs to DRAM. We want to minimize random IOs to DRAM from GPU instead of just random IOs to disk from DRAM. And that's one of the reasons I wanted to jump on this project, because it seems like you all are working on really awesome, sophisticated new architectures, including all sorts of data access patterns And some of these physics-based models have very unique access patterns that are much more sophisticated than these feed-forward models. And that could lead to new computer science techniques. So it's not going to be just applying our software to you in a straightforward manner. We might need to extend the science from the computer science standpoint as well. Okay. So yeah, so long story short, it's not a solved problem. It's a new, exciting space. There's going to be a lot more research that is needed across the levels of the hierarchy. And we are doing some of it. Hopefully, I'm hoping some of the other folks in the database and systems world and ML world also jump on board and start contributing to this sort of stuff.
Cool, thanks.
Okay. More questions?
So maybe I maybe I want to ask a question, maybe not directly related to the talk, but just the general questions on graph. Have you seen any work that dealing with, is it possible to, do you see any graph neural network work that that have a hierarchical nature? Like what I mean is that, for example, on direct graph at the very high level, but inside each node there's a subgraph that a direct graph. Is there anything similar in the computer science domain?
Okay.
Did I explain myself correctly? So.
Oh, that's a great point, WaiChing. I hope I'm pronouncing your name right. It's WaiChing, right?
Yeah.
So in the computational graph architecture space, there's a lot of innovation happening. One of the things I've heard from some of these people who are coming up with these newer architectures is TensorFlow and PyTorch itself are no longer sufficient for some of their architectural innovations.
Oh, okay.
The APIs they provide for specifying the computational graph itself is no longer enough. They're coming up with new ways of composing layers. Some of these researchers are actually baking in what we call discrete optimization methods. So these are like combinatorial optimization methods from computer science theory that alongside the convex or the non-convex optimization that these tools support to be kind of interleaved. These tools don't let you do that today. You have to write arbitrary code yourself in lower level Python or just C++. However, I've heard from these companies, Facebook and Google, that are contributing to the production of the next generation of these software systems, that they're actually working on a new programming language for differentiable programming. So differentiable programming is a paradigm of computer programming that generalizes this idea of deep learning. And you do this for programs that operate on more general things. So like graphics or simulations or game playing or whatever. And all of these programs are differentiable automatically and trainable using stochastic gradient descent. And the idea is differentiable programming will allow you to write a new programming language that looks kind of like Python, but it's not hemmed in by the limitations of Python itself, so that you could now come up with better compilers and better executors for them.
I see.
So that's the hope. So right now, if you're coming up with architectures that don't subscribe to their APIs for specifying computational graphs, you're out of luck. Hopefully, in the next few years, with a new tool that generalizes this differentiable programming paradigm, it will improve the state of the life for deep learning practitioners, or even non-deep learning general differentiable programming practitioners.
Yeah.
Does that help?
Thank you. Yeah, that's helpful. I also want to ask another experience, maybe I should ask more related questions. But what is the major motivation to drive one computer scientist to use the PyTorch over TensorFlow and vice versa in general?
Good question. Let me do a quick show of hands. How many of you like PyTorch? How many of you have used PyTorch? Say yes. And if you prefer TensorFlow over PyTorch, say no. Let's do a yes or no on the Zoom thing. Yes, if you say yes for PyTorch. No, if you say you like TensorFlow better.
No. I only tried TensorFlow, so I don't know the other side. So that's why I'm curious.
The audience is not participating in the yes or no. That's very familiar to me. My students are like that too. Students participate in the yes or no questions. So yeah, I mean, it seems like there's a flame war going on between TensorFlow and PyTorch, and flame wars are very common in computing. Like there's the editor war, Vim versus Emacs. And in the data science world, there's the Python versus R war that did a few years ago. Python won, R lost, unfortunately. If some of you are R fans, unfortunate for you. I used to work on R as well a few years ago. And then I pivoted to working with Python. From my research standpoint, I don't really care what the programming language is. R, Python, I focus more on the abstract computational principles. Now, coming to your question between PyTorch and TensorFlow, why do people prefer one over the other? PyTorch is overwhelmingly preferred by domain scientists as far as I can see, and also by AI researchers, because its APIs are just more intuitive for them. It allows for more complex and custom models. TensorFlow is overwhelmingly preferred in industry, especially in enterprise industry, because TensorFlow's ecosystem is far richer and far stronger for production strength, like model deployment, model debugging, and stuff like that. PyTorch is an open source project. It doesn't have the heft of something like Google backing it that much yet. That said, in the last year or so, the gap has been narrowing. TensorFlow now has TensorFlow Eager and all of those kinds of APIs that allow you to do all sorts of fancy computational graphs as close to PyTorch's parsimony as possible in writing code. So the gap is narrowed on that. Keras has been absorbed into TensorFlow.
Yeah.
So that gap has also narrowed. Keras has become a lingua franca for deep learning platforms. It supports multiple of these under the hood anyway. So a lot of practitioners don't really care about this distinction as much anymore. And on the industrial strength stuff, PyTorch now has backing from Databricks. I spoke with Mate Zaharia. He visited my class last fall. MLflow is a tool that is backing PyTorch a lot. And some of the industrial strength infrastructure that TensorFlow has, they're replicating it for PyTorch. So that gap has also narrowed. So yeah, coming down to this, it's like one of those flame wars, C++ versus C#, Emacs. And so that's why from my standpoint, I'm like, I don't care which one you pick, I will support both. Because from the computational standpoint, they basically do the same thing, which is computational graphs, stochastic gradient descent, and then the scalability and the principles are all pretty general, regardless of what framework you use.
Yeah, thank you. Yeah.
More questions?
I think I mean, I have a quick question. I know it's already past 11 and people already feel free to leave. Just a quick question that I heard a lot of also about this federated learning nowadays. What's the relation? I mean, does the framework would work for that, or it's very different mechanism one should design different ways to handle?
Oh, you mean federated learning?
Yeah, that's right.
Okay, great. Yeah, so federated learning is, you can think of this as something that doesn't do it on, say, a cluster or a cloud. So like here, for example, I'm saying you're doing this cluster or cloud. The paradigm of federated learning, and I teach this in my ML systems class too, instead of take these away and then put devices, end user devices like smartphones, Internet of Things devices, and so on. Those will be your computation platform for training bits and pieces of the model on bits and pieces of the data from the user. And so basically the people who are using smartphones, if they want to train their autocorrect on their data, then Apple, for example, will use federated learning to train a part of the model on your device and then periodically send aggregated gradient updates or weight updates to the server that sits in the cloud. And so federated learning has become common for very privacy sensitive applications or very personalized oriented applications in industry, especially for the consumer sector, for companies that sell smartphones and software on smartphones, like Apple and Google. And Facebook, I don't think uses federated learning as much, but Google and Apple are especially heavy users of federated learning. And in the domain science regime, I don't see that many use cases for federated learning, because I don't think that many domain scientists operate with smartphones or Internet of Things devices. I don't think agencies like NIH will fund that scale of projects either. If you're going to say, I'm going to do a project with 1,000 people and everyone is going to have a smartphone app, I highly doubt federal agencies will fund that. So it's just the nature of the way science rolls. That said, there are people in IoT space who do federated learning, and they're doing research, especially in economics and logistics and policy, like GPS here on campus. There are people who are interested in getting smartphone data to do these sorts of research. So some of that could potentially be helpful. Now, Cerebro doesn't have federated learning in its vision right now, but the elasticity and the fault tolerance aspects of Model Hopper Parallelism potentially means it could be generalized to that regime, because it is decoupling the computations on different workers instead of tightly coupling them. it's what we call asynchronous computations. Federated learning is naturally asynchronous. So I think there's an interesting systems technical connection there. We haven't looked into it, we haven't prioritized it, but if I find some use cases and workloads that are real that I can have access to, then I'm open to it.
Great, thank you.
Okay.
Yeah.
Great question. Yes, Hendrik, you had more questions?
I think there could be more follow-up questions. Right now, actually, I'm still digesting the material. It's very interesting with the sharding and the efficiency improvements and what Cerebro does. So I think I'm good for this time. I mean, if there are no more questions, then maybe we are. I want to thank everybody again for attending. And yeah, we'll see you soon, or see you next time for the next.
See you in the next meeting. Happy spring break, everyone. And
Thank you, Arun.
Yusu, Hendrik, are you going to post this video somewhere and then let me know where?
Yeah, it's
Yeah,
on the conference website.
Yeah, we'll post it on
Of
YouTube.
the-
So
Sorry,
so I'm-
seminar. Yeah.